So now that we have set up the entire simulation, we want to go ahead and run it. So we save. That generates this in file, which is what the simulation actually reads. And you can look through that and see all the details if you want. But it's essentially just a summary of all the things we set up visually. Then we click Run, and we can see we have a few parameters for our run. We have a time step, which we specified. We have the number of steps that the simulation is going to run for. That's set to 15,000. But we changed that to 4,000 during the setup. So if I hit reset to setup values, we can see that switches to 4,000. And we're going to dump data every 500 time steps. So in the end, we should have 8 data dumps. We can then choose to dump at time 0. This will dump our initial conditions. We're going to run in parallel just on 4 cores. And so we can go ahead and hit run, and we'll see the simulation start to run. And most of this output will be things like setup, and then now we can see it's taking steps and doing the reactions that we specified. All right, we can see the simulation is now finished. It did all 4,000 time steps and exited without error. So we can go on now to visualize the data of the simulation we just ran. So we go over and click on Visualize, and it loads the data files. In the Visualize window, we have multiple options for the data we want to see. So we can click this drop-down menu, and we have Data Overview, Histories, Phase Space, and Binning. So we'll start with Data Overview. And here we'll just be able to see the raw data. And in this simulation, all we have is argons to look at. So we can look at the argons, and we see at dump 0, time 0, this is our initial condition. We have the argons equally spaced across our simulation domain. And as I click through the time steps, we can see that the particles evolve in time, and we can see some overall characteristics of the argon as well. For instance, that on the left side of the domain, the argons are more dense, and on the right side, we see they're spaced out more. And this is due to the physics that's going on. On the left side, we have a cold plate, so these argons over here are colder. And on the right, the argons are warmer. And because of the ideal gas law, we know this whole simulation is at a constant pressure that we set. So when we have higher temperature, we will have lower density, and vice versa. When we have lower temperature, we will have higher density. So this qualitatively behaves as we would expect. We can look at the phase space and see this in a different way. So if I plot on the x-axis just the x distance, and on the y-axis I plot the x velocities, we can see at the beginning of the simulation we have fairly evenly spaced argons. The height of this distribution is roughly constant all the way across our domain. So that means that this is roughly all at the same temperature. If I click through, we can see that on the left, again, we have higher density, on the right we have lower density, but we can also see the temperature on this graph, because the temperature of a species like this is indicated by the width of the species in this velocity space. So where we have lower temperatures, we have a narrower range of velocities. And on the right side, where we have higher temperatures and lower densities, we can see the velocity range is spread out much more across this axis. Lastly, let's go and look at the histories that we recorded. We asked for some specific histories. We can see our first history is the just total energy of the argons. And I said earlier that we didn't need to run for all 15,000 steps to reach equilibrium. And we can see that here, that after just an eighth of our simulation, we've already reached some sort of equilibrium where the argons are giving away just as much energy as they're receiving. And so we have some constant energy across our gas. The more interesting bit is these energies that are exchanged between the particles and the boundary conditions, the plates. So we have the energy from the cold plate, and we can see that's negative because this is the energy transfer from the plate to the particles. And since this is a cold plate, we expect the energy to be given from the particles to the plate. And vice versa for the hot plate, the energy exchange is positive. Now, this is actually a plot of the power that's transferred to the plate. So this is energy per time. So this is not dependent on the time step we chose in our simulation. So it's a physical parameter. Now we took this average here, and this average is what we can compare to theoretical values. So I'm going to get rid of some of these plots so we can see the average more clearly. It's noisy because the particles are moving around and hitting the plate in a statistical way. So we will have some time steps where not many particles hit the plate and other time steps where more particles hit the plate. But we can see that it's oscillating around some value here. And this is something around 5 watts. And we can compare this to the actual results, the analytical results, and we can look at this in the help. So if we go to help, VSim examples, we're in the plasma discharges, and we go down to other, and then to the neutral heat transport. We can see this kind of gives you a walkthrough of how to run the simulation, but down at the bottom, we have a plot of the theoretical values versus what VSim obtains. And so let me explain this plot just a little bit. On the x-axis we have pressure, and this is one of the parameters we set at the very beginning of the simulation. We set it to 0.2. And then on the y-axis we have heat flux, and this is watts per square meter. So what we just saw on this visualize was watts, so about 5 watts, let's say, for this simulation. But this is heat flux, so it's watts per square meter, means we need to divide by the surface area of the plates that this energy was exchanged with. If you recall, back in the parameters section, we set the width of the plate to be 0.2. This is a 2D simulation, so that means we can say the area is 0.2. So if we take this watts, about 5, divide it by 0.2, that should give us about 25 watts per square meter, and that should put us somewhere on this green line. Now obviously we did that just on back of an envelope calculation, but you can run the Python script that comes with this simulation, and it will plot your data on this graph. And regardless of the pressure you chose at the beginning, you should find that the red X, the simulation data, always lies on this green line. On the left side, this is very non-collisional. It's low collisionality gas, low pressure, so the collisions are essentially non-existent, and all this orange line indicates is kind of like a free streaming, just particles hit a plate, they go across and hit the other plate without colliding in between. As the pressure increases, our collisionality increases, we expect collisions to occur, and so you can imagine that it takes longer for the argons to get from one plate to the other plate, so the heat flux slows down, and that is what we see and what we expect. The blue line indicates the highly collisional regime, so at arbitrarily high pressures we will not increase the heat flux at all just because the particles are colliding so much. The importance of this example is that then it verifies the correctness of the collisional algorithms in the code. We hope you enjoyed this example and it was helpful for you. Thanks for watching, and look for our other example videos.